With Pavel Kovtun of the University of Victoria. I'm Brian Swingle. I'm a co-organizer for the Aspen workshop on hydrodynamics and quantum matter. Of course, we plan to share new physics this summer in Aspen, but that's not possible right now. However, we can at least bring you a flavor of what was going to be discussed there here in this venue. New this year, the Colloquium will be posted on YouTube at Aspen Physics, and you're invited to share this talk with your students and colleagues. The center is also hosting public lectures online on Thursdays at 5:30 Aspen time, which you're invited to join. Since Pavel's talk is only about 40 minutes today, we are not going to interrupt him, but please raise your hand by clicking on the hand button at the bottom of your screen, and I call on you during the question and answer period, which will just follow right after the talk. Also, the talk is being recorded. You may appear in the recording, so you can stop your video if you don't want to be seen. Now a little bit about Pavel and his work. People have been trying to understand the motion of fluids since ancient times. For example, if you want to build a ship or a windmill or an airplane, you need to know something about hydrodynamics. Hydrodynamics also plays an important role in modern physics, for example, helping us understand the motion of electron fluids in quantum materials, the motion of the quark-gluon plasma, and even the dynamics of black holes. Our speaker today, Professor Pavel Kovtun, is an expert on hydrodynamics who has contributed significantly to many of these exciting recent developments. He got his PhD at the University of Washington in Seattle and was a postdoc at the Kavli Institute for Theoretical Physics in Santa Barbara before joining the faculty at the University of Victoria in Canada. When I first encountered his work as a graduate student, he was already quite famous for something called the KSS bound. He's the K in that. A proposal that there was a fundamental bound on how viscous a fluid can be. And this proposal generated a lot of excitement in fields ranging from string theory to cold atom experiment. So that was really cool to see the coming together of these different communities. More recently, he continues to make foundational contributions to the theory of hydrodynamics, including topics like the regime of validity of the theory, which I think he'll tell us something about today. So as I said, Pavel was going to be in Aspen this summer at the meeting that my colleagues and I had organized. So we're very grateful that Pavel has agreed to give this glimpse into his really exciting work at this unconventional format. So without further ado, Pavel, take it away, and then we'll have questions and answers at the end of his talk. Thanks.
Well, thank you very much, Brian, for the introduction. I'd like to begin by thanking the Aspen Center for Physics and the program organizers for maintaining the Colloquium series during these difficult times. And of course, I'm very happy to participate and to contribute. So I'll be talking about hydrodynamics. So it is an established field, of course, with a venerable history and many applications. However, today I will not talk about applications. Rather, I would like to highlight some foundational questions that only came to light in the last few years. So a better title for my talk perhaps would be Hydrodynamics, a Theoretical Physicist's Perspective. So what is hydrodynamics? Basically, it's a set of equations that tell you how stuff flows, okay? So this stuff that flows, this could be water, air, could be a cold atomic cloud, could be hot primordial matter in early universe, could be electrode fluid in a solid, etc. So let's say you're a student. And as a student, you open a book with hydrodynamics or fluid dynamics in the title. And from my own experience, I remember that, I usually would see the derivations, approximations, and applications, and they will all be mixed together. Right? So if as a student, you're also trying to learn about vector calculus and partial differential equations at the same time, it can be difficult to see the big picture. But the big picture of hydrodynamics is in fact quite simple. So hydrodynamics essentially is a macroscopic theory of things that cannot disappear, that is, they're conserved. And the way we write down conservation laws in physics is like this. So this equation. So in the right-hand side, you have a time derivative of some conserved density, so density of some conserved quantity, which I call little a, And in the right-hand side, you see the divergence of the flux of that same conserved quantity, right? So this equation we teach to our second-year students in electromagnetism when we talk about the conservation of charge. We teach them when we teach quantum mechanics and talk about the conservation of probability. Of course, exactly the same equation. Here we teach our students in fluid dynamics when we talk about the conservation of mass. So this applies to all useful conserved quantities, and so this little a can be energy, momentum, number of particles, and whatnot. So there is one more ingredient that you need in hydrodynamics. It's called the constitutive relations. So if you look at this conservation law right here, so then you see it's basically one equation and there are four unknown functions. So one unknown function is this density rho that sits on the left-hand side, and this flux is a vector, and in 3 dimensions, vector has 3 components. So you have 3 unknown functions here and 1 unknown functions here. Have 1 equation, 4 unknowns. There is not much you can do. However, if you assume that the flux is a function of the conserved density, then you have a single equation for a density, and then you can solve. Right? So this relationship between the flux and the density is what you call the constitutive relation. So more generally, you can take some useful quantities, which I will call gamma. So my useful quantities will be temperature, fluid velocity, whatnot, and express the density and the flux in terms of those useful quantities. And then you have only equation for those useful quantities, which you can solve. So just to give you an example of how this works in practice, so let me take my conserved quantity to be energy, my useful quantity to be temperature. So then when I write my density as a function of my useful quantity, this means I write my energy density as a function of temperature. So we know what this is from the equation of state. And then we also need to express the flux, which is a vector, the energy flux, in terms of temperature. Now, the way you do it is you say the energy flux is a vector and temperature is a scalar. And the simplest way to make a vector out of a scalar is to take the gradient with some coefficient here. So if this coefficient is positive, this would tell you that energy flows from regions where it's hot towards regions where it's cold. And then it's pretty easy to see that once you substitute this into the conservation law, you get the diffusion equation, right? So 1 derivative in the left-hand side and 2 space derivatives in the right-hand side. Okay, so that's how you derive the diffusion equation. So this is basically the summary of hydrodynamics, all you need to know about hydrodynamics for the purposes of today's talk. There are 2 ingredients. One is the conservation law, and one is the constitutive relation, where you express the densities and the fluxes in terms of temperature, fluid velocity, and whatnot. And the procedure is exactly the same, whether the fundamental ingredients are quantum or classical, relativistic, non-relativistic, normal fluid, the superfluid, whether you have magnetic fields or not, you work with magnetohydrodynamics or not, you have a chiral fluid or not, so it does work exactly the same. All right, so here is a summary of hydrodynamics. So conservation laws, constitutive relations, and of course in physics, we try to simplify things as much as possible. And the first simplification that you do is you just take all the terms that have, derivatives of your useful quantities, and you just by hand, you throw away all the terms that have those derivatives. And if you just do this, just by hand, throw them all away, you get what you call, quote unquote, perfect fluids. So the corresponding equations are called the Euler equations of hydrodynamics. If you, by hand, just throw away all the things that have 2 and more derivatives, you get what is called viscous fluids. And the corresponding equations are called the Navier-Stokes equations of hydrodynamics. And again, if you just by hand throw away all the things that have 3 or more derivatives, you get what you call second-order fluids, so-called Burnett equations of hydrodynamics. So this is hydrodynamics. So it's been around for many, many, many years. And well, it's a physics theory. And as we know, every physics theory is wrong, or rather it is only approximately correct within its domain of applicability. And just like with every theory, we have to ask questions. We have to question our theory. So in particular, we have to ask these questions. So do our equations make physical sense? Can we improve the equations to capture more physics? And what kind of physics is beyond our equations? So what I'm going to tell you today are 3 short stories. There is going to be 1 story for each of those 3 questions. All right. So my first story is this. Do hydrodynamic equations even make sense? Okay, so that's maybe you think is a strange question to ask. Well, it's not so strange. So for my first story, I'd like to think about things that are relativistic. So let's say you're a student who works in subatomic physics or maybe astrophysics, and you want to learn about relativistic Navier-Stokes equations. Say you want to understand the quark-gluon plasma, or maybe you want to understand neutron-star mergers. And you know, in the old days, there used to be this thing called books. So now libraries have thrown away books for the sake of digital literacy, but you know, books still do exist. And you know, if as a student you open a classic textbook on fluid mechanics by Landau Lifshitz, you will see some hydrodynamic equations in there. Well, you can open a different book, say Gravitation and Cosmology by Weinberg, and you will also see some relativistic Navier-Stokes equations in that book. So those equations are due to Eckert. And then you compare them and you see they look very different. So equations in Landau Lifshitz, they look very different from the equations you see in Weinberg. So as a student, you are probably confused. However, as a student, you're also taught to just shut up and calculate. Okay, so let's just shut up and calculate. So as a simple example, what you can do, you can just solve for infinitesimal small linear perturbations of the thermal equilibrium state. And when you do this, you will find two things. You will find that the equations of Landau, Lifshitz, and Eckert, they're different equations, but they predict two things. One thing they predict is that they predict that thermal equilibrium does not exist. And the second thing, they predict that things propagate faster than light. Okay, so this is kind of embarrassing. So it's not a joke. These equations do predict those things. So it's sad but true. The equations that you find in the classic textbooks, they make no physical sense. And this has led to the belief that the Navier-Stokes equations, they cannot be unified with Einstein's relativity, and they have to be abandoned in a relativistic setting. And other exotic theories have been proposed in the 1970s to replace the Navier-Stokes. The field has moved on. But as a student, you know, you still have this nagging question. So why do the theories of Landau, Lifshitz, and Eckert, why do they differ in the first place? So to understand why, let's talk about temperature first. So I'll let you read this XKCD cartoon. Okay, so clearly some subtleties about temperature. So let's talk about temperature. So temperature is something that is only unambiguously defined in equilibrium. And by definition, temperature is the quantity that is measured by a thermometer. And what I have here is a cartoon of two different thermometers that are immersed in the same equilibrium state. So this orange stuff, orange box, is my stuff in equilibrium. The red blob and the green blob are two different thermometers that are coupled to their gauges. And if the thermometers are properly calibrated, then in identical equilibrium states, these two different but properly calibrated thermometers, they will show exactly the same temperature, right? That's the whole point of calibration. Now, however, let me now take the same two thermometers and place them in identical non-equilibrium states, okay? Now there's something that's happening here, but these are two identical non-equilibrium states, and I place the same two thermometers in those identical non-equilibrium states. Now my thermometers will show different temperatures. And of course, it's easy to understand why. You know, the heat conductivity of these walls may be a little bit different. The property of the red material and the green material may be different. The shape of these thermometers will be different. So in general, these thermometers will show two different things, even though they used to show the same thing in equilibrium. So what this tells you is that there is a certain degree of arbitrariness or a convention. So there's a certain arbitrariness of what you mean by fluid temperature when you are out of equilibrium, because your choice of a thermometer is a convention. And so there is also the same arbitrariness of what you mean by fluid velocity. So your choice of velocimeter is also a convention. And Landau-Lifshitz version of Navier-Stokes equations, so they use one convention, and Eckert uses a different convention, and so that is why the two equations are different. And so what is important to emphasize here is that there is no such thing as so-called the Navier-Stokes equations until you specify your arbitrarily chosen convention. Okay, and this is just because you're supposed to describe a situation which is not in equilibrium. Now, so this is something that's very important to remember. So different conventions give rise to different mathematically inequivalent Navier-Stokes equations. So the conventions have real consequences. So it's not a typo. So different conventions will give you Navier-Stokes equations that are mathematically inequivalent. And this is because the Navier-Stokes equations only give you a crude approximation of a real fluid. So the difference between this convention is hidden in the crudeness of this approximation. So Landau-Lifshitz and Eckert adopt different conventions for Navier-Stokes, and both conventions are bad, and they both lead to nonsensical predictions. So what exactly is wrong? So the easiest way to understand this is the following. So both Landau-Lifshitz and Eckert, they define temperature by this equation. So they say that the exact non-equilibrium energy density is given by E of T, where this is the energy density as a function of temperature given by the equation of state, right? And remember, E, energy, is the real thing, and temperature is just a proxy for energy. And so if this is how you define temperature, this means the following. As the local energy density changes, the thermometer adjusts its temperature instantaneously, okay? And such thermometers that react instantaneously, they violate relativity and lead to superluminal propagation in relativistic fluid dynamics. So this is why the equations of Eckert and Landau-Lifshitz make no physical sense, and that's why they have pathologies. So you can say, wait, well, okay, so it's that simple, and it is that simple. Why don't you choose a thermometer or velocimeter that does not react instantaneously and respects relativity? So can you just adopt a sensible convention? And the answer is yes, you can. With good conventions, the equilibrium is stable, signals propagate slower than light, the equations are mathematically well posed, they can be coupled to Einstein's equations of general relativity. And you can look at details in this paper, and you see these developments are relatively new. It's only last year. So the bottom line is this: so unifying Navier-Stokes with relativity was thought to be impossible for many decades, but that's just because maybe you haven't thought of your conventions carefully. You just need to choose a physically sensible thermometer or velocimeter, and then the Navier-Stokes equations are happily unified with relativity. And they're still waiting to be solved. So those equations, as I said, they are just fairly recent, and they're still waiting to be solved. And the lesson for students is this. So if you're reading the classics and they don't make sense, okay, just rederive everything using your own way, and you may discover something new. So that was my first story about how to think carefully whether your equations may or may not make sense. So my second story is this. So are there limits to improving the hydrodynamic equations? So let's take a first look at the limitations of hydrodynamics. So hydrodynamics is a macroscopic description, but of course there is also the microscopics, right? So a fluid is made out of some stuff, which are schematically represented here by these blue dots. So think of particles. And there is typical, distance scale associated with the separation between those particles or constituents of your fluid, so I call this small l. And on the other hand, if you look at the solutions to your fluid mechanical equations, so how temperature or the fluid velocity changes as a function of distance, so you will see there's another scale, the capital L scale, the macroscopic scale of your solution. So this capital L can be, say, the wavelength of your sound wave or the size of your pipe or whatnot. And hydrodynamics is probably okay when capital L is much bigger than small l, meaning when the derivatives of this blue function are in some sense small. So on the other hand, suppose that you solve your hydrodynamic equations and you find that your temperature or the fluid velocity they look like that. So the scale, the variation scale, capital L of your solution is kind of the same as the interparticle distance here. Then you say, well, you should not trust the solution. So hydrodynamics is not okay when capital L is approximately the same as small l, meaning when the derivatives of this function are large. So what this tells you is that the simplest way to think about hydrodynamics is an expansion in derivatives. So remember what hydrodynamics is. It's two things. It's conservation laws plus the constitutive relations. And the way I'm writing down my constitutive relation here, I'm writing this down as an expansion in derivatives. So the first terms that I denoted with superscript 0 is something that has no derivatives. Second term, which has superscript 1, has one derivative. Something with superscript 2 has two derivatives, and so on. Okay. So if you only look at the first term here, this is what you call perfect fluids. Of course, perfect fluids is the most imperfect model of fluids. So these fluids cannot flow through pipe. Sound propagates forever. So if I say something here, everybody can hear me 10 miles away. Diffusion does not exist, so on. So if you look at the first two terms in this expansion, that's what gives you the Navier-Stokes fluids. So it's an improvement. It's an improvement of the perfect fluids. So you introduce dissipation and restore common sense. You can also look at second order fluids, which would be an improvement of the Navier-Stokes fluids, and so on. Now, so once you see this, I mean, there's one very natural question that you can ask. So can you keep improving forever? So let's say you generate an infinite series in these gradients. So does the series converge, as in this example, when you sum 1 over n squared and you get a finite answer? Or does the series diverge when you sum 1 over n and you get infinity? But in both of these examples, each subsequent term is smaller than the previous one. But in the first case, you get a sensible finite answer. And in the second case, you have infinity. So is hydrodynamics like this? Or is it like that? So, and if the series converges, this means that hydrodynamics can be systematically improved to include more and more transport phenomena. And if it diverges, well, there are really more questions than answers. So hydrodynamics is really not supposed to work. Then why does it work? Is the very existence of hydrodynamics a fluke to begin with? So how do we look at this question? So what exactly is the expansion? So let's look at the simplest case, which would be a plane wave, right? So in second year physics, we teach all of our students that waves should be represented by complex exponentials. Okay, so I represent my wave by a complex exponential, say a sound wave, in which case the derivative is just a power of the wave vector, right? When you differentiate this with respect to x, you bring down a factor of I times k. So the expansion is the expansion in powers of k. And if you look at, say, in this plane wave, how the frequency of your wave is related by the wave vector, so this so-called dispersion relation. So for sound, it looks like, there's the linear piece, which is what we teach in first year physics of waves. So then there is also a piece that is proportional to k squared with some coefficient that is proportional to the viscosity and determines for you how the waves dissipate. So you see it's proportional to k squared, meaning long wavelengths wave dissipate less. So that's why it makes sense to use longer wavelengths for underwater communication, for example. So you ask this question, so does the series, which will have k and k squared and k cubed and so on, does the series converge or diverge? So this question is actually a very difficult question. So let's say you want to compute this coefficient b. Right, so okay, so this a is speed of sound. Speed of sound you can find from the equation of state. So let's say if you use the ideal gas equation of state, so that's quite straightforward to find what this a, so this a is just the speed of sound, what this would be. But now if you ask about b, b is the viscosity. So if you look at the ideal gas, the viscosity of the ideal gas is in fact infinite. So the ideal gas is as far from the perfect fluid as you can get. Okay, so let's say you don't have an ideal gas, you have a near ideal gas, almost ideal gas. Can you compute this? B? Well, if you look at the fundamental interactions in physics, such as the standard model of particle physics, then this computation of B was only done correctly in the 21st century. Okay, so it's not something that's very easy to compute, right? And now I'm asking not just about B, I want C and D and so on, and I want to know if the series is actually convergent or divergent. So this is a very difficult question. So you don't know how to answer this in general, but we can look at simple examples. And there are some analytic examples. So there are fluids that can be studied analytically using methods of so-called holography. So if you know what holography is, good. If you don't know, don't worry about it. This is just some exactly solvable fluids. So these fluids are similar to the quark-gluon plasma that is produced in nuclear collisions. Not exactly the same, but sort of like that. And in the simplest solvable examples of those fluids, you find this sound wave dispersion relation. It is indeed an analytic function of the wave vector, which is convergent within a finite radius that is determined by the temperature. Okay, so the convergence, so there's some number, some square root of 2, which is quite nice. So the convergence qualitatively is important. So it gives you hope that hydrodynamics is improvable. Okay, so I told you that these things converge, but I didn't tell you why. So I didn't tell you why there is a critical value, why there's a critical wavelength or a critical wave vector. And to understand why, so let's look at a simple example from basic math. So I want to look at a function that looks like this. F of x is 1 divided by 1 plus x squared. So this function is plotted here on the left. And this function is perfectly smooth for all x from minus infinity to infinity. But let's say you want to write down an expansion for this function when x is small, when x is in the vicinity of 0. So the Taylor expansion for this function only converges when x, absolute value of x, is less than 1. Okay? Now you look at this function is perfectly smooth. X is equal to 1 is here. Function is perfectly smooth. But the Taylor series only converges when x is less than 1. So why is that? So the reason, of course, is that you need to take x complex. And when you take x complex, then you see that this function, even though it's perfectly smooth when x is real, it actually is singular when x is imaginary. So this gives you the finite radius of convergence. And so the same thing happens in fluid dynamics. Your dispersion relations, the frequency of your wave as a function of the wave vector is a smooth function for real wave vectors. And to understand why they only converge within a finite domain, you must take your wave vector complex. So let's take about complex frequency and momenta here, wave vectors here. Right? So in classical physics, all the dispersion relations, they come from solving equations that look like this. So some capital F, some function of omega and k squared is equal to 0, where this F is determined by whatever equations you're solving. So equations of hydrodynamics or Maxwell's equations in matter or whatnot. And say in the diffusion equation, which I talked about earlier, you see exactly how this shows up, right? So this is your diffusion equation. You take your temperature to be a plane wave. You differentiate this once with respect to time, you get minus I omega. You differentiate this twice with respect to x, you get minus dk squared. So that's your capital F for the diffusion equation, right? So if you look at sound waves, the equation looks slightly more complicated, where this Vs is the speed of sound, this capital gamma is proportional to the viscosity. Okay, but morally speaking, there's some function capital F that will determine for you the relationship between the frequency and the wave vector. And in physics, we usually do one of two things. One thing we do is we take our frequency to be a real number. And then you solve this equation and you find the wave vector as a function of frequency, which is in general complex. And the imaginary part of your wave vector is now interpreted as the damping length or the penetration depth for the wave. So another thing that we do in physics, we take our wave vector to be real. Then you solve this equation and you find frequency as a function of k, which is in general complex. And then the imaginary part of this frequency is interpreted as the relaxation time. Well, what if both omega and k are complex? So that's not something we normally do in physics. In physics, we only take one or the other to be complex. I want to take both complex and see what happens. So this is an example of the oscillation modes in a fluid in those exactly solvable examples that I talked about. So each dot in this plane, so this is a plane of complex frequency, real part of frequency and imaginary part of frequency. My frequency is measured in the units of temperature. And each dot in this plane represents a solution to this f is equal to 0. In other words, it represents an oscillation mode of your fluid at some value of the wave vector. Q is basically the wave vector in units of temperature. Okay. So these two dots, the gold and the blue, which are the closest to the origin, these are the sound waves, whose relation between omega and k is like this. So there's a macroscopic classical excitation. They approach the origin as the wave vector goes to 0. And the other things, they are microscopic oscillations. They have no classical interpretation. They stay away from the origin as the wave vector approaches 0. Okay. So this was when the wave vector was real. Okay. So what you're looking at is exactly the same picture where the wave vector is real, and now I want to make it complex. So what I'm going to do is I'm going to take my wave vector and I will add a phase to this q squared. Okay, and so this is the picture that you see when the phase is equal to 0. Now I'm going to change this phase from 0 to 2 pi. Okay, and as I change the phase from 0 to 2 pi, the dots, the modes of my fluid are going to move in the complex plane. And as the phase changes from 0 to 2 pi, what you see is like that. Okay. So the blue and the gold, they have swapped places, so it's easier to understand why that happens. But they still remain sound modes when your angle goes back to 2 pi. Of course, the set of modes has to come back to itself when theta is equal to 2 pi. Okay. So now what I'm going to do, I'm going to look at my oscillation modes of my fluid when my wave vector is not equal to 1 in units of temperature, but when q squared is 1.99 in the units of temperature. And again, I'm going to change my phase from 0 to 2 pi and see what's going to happen. So when the phase changes from 0 to 2 pi, so that's what's happening. Okay, there is some complex motion. So the blue and the gold, which are the sound waves, they still remain sound waves. They still remain the modes that are closest to the origin. If you take the wave vector to 0, they will still approach the origin. So now my last movie will be not when my wave vector is equal to 1.99, but when it's equal to 2.01. And as the phase changes from 0 to 2 pi, so that's what happens. So see now this gold dot, which used to be a sound wave, it becomes one of the non-classical modes. So it's not a sound wave anymore. So if you look at the trajectories of how the modes move in the complex frequency plane, so these are the two trajectories when the wave vector is equal to 1.99 and when the wave vector is equal to 2.01. Okay, so you see there's a change in topology, right? So where I have this little star here is where a collision would happen when the wave vector is exactly equal to 2. So when it is equal to 2, the modes collide and the topology changes. So what you're looking at here is you're looking at level crossing, but it's not level crossing in simple quantum mechanical examples. It's level crossing in macroscopic dissipative systems, when a classical excitation becomes a non-classical excitation. And so this is what determines this level crossing, and the disappearance of a classical excitation into a non-classical excitation at complex wave vector is what determines the convergence of the expansion and what gives you the critical wavelengths for sound. There's actually more to complex momentum. So unfortunately, I will not have time to talk more about this, but there's a fascinating relationship between complex momentum and chaos. So chaos is, well, it means different things to different people. So the easiest way to think about chaos is perhaps how microscopics gives rise to macroscopics. And the way, one way to describe chaos in classical mechanics is through the so-called Lyapunov exponents that describes the divergence of phase space trajectories in as time goes on. So this lambda that sits in the exponential is something that tells you about the rate of divergence for your trajectories. And there exists a quantum mechanical analog of the Lyapunov exponent, and that quantum analog involves a commutator of two operators. And you take the average of the square of the commutator in thermal equilibrium state, and there is again some exponential growth in time. And so there are arguments that tell you that this lambda is basically a quantum version of the classical Lyapunov exponent. So let me do something that's very, very silly, okay? So let me take a plane wave, a complex exponential, and let me take omega to be equal to I lambda, some purely imaginary thing. And let me take my wave vector to be, again, purely imaginary. And then my plane wave becomes something that exponentially increases with time, okay? So this is, of course, a very silly thing to do, but in many solvable examples of the same kind that I was talking about, this can be made very precise. And it turns out that the dispersion relation for sound waves at complex wave vector, they actually know about the Lyapunov exponent, the quantum Lyapunov exponent. So if you look at the dispersion relation of sound waves, you can actually find what the quantum Lyapunov exponent is, and you can just characterize some quantity that relates to quantum chaos purely from hydrodynamics. So that's actually quite fascinating. So the bottom line is this. So in many solvable examples, classical macroscopic excitations and non-classical micro excitations, they're just two different branches of the same multivariate complex function, like the function square root of z has two branches, right? So here you should be thinking about classical and non-classical things as just living on two different branches of the same function. And another fascinating lesson is that in many solvable examples, classical hydrodynamics at complex momentum, it knows about quantum chaos through the quantum Lyapunov exponent. So this is the end of my second story. So now I come to my final story. So my final story is going to be short. It's going to be this. So why everything I said so far is wrong. Okay, so I want to take a second look at the limitations of hydrodynamics. So my second look at the limitations of hydrodynamics is this. So macroscopic stuff is made out of microscopic stuff, so it's clear. So microscopic stuff is not simple, even if it is just the vacuum. So in a quantum vacuum, virtual particles are constantly produced and absorbed due to quantum fluctuations. Similarly, in a macro state, virtual sound waves are constantly produced and absorbed due to statistical fluctuations. And just like the quantum fluctuations in the vacuum back react onto classical fields, so these virtual sound waves will back react on the macroscopic physics. And that is because hydrodynamics is a nonlinear theory, so waves interact with each other. So this is a cartoon when a micro excitation produces sound waves, and the sound waves will back react onto what I thought was my sound wave. So is this back reaction even relevant? So before you think that it is totally and utterly irrelevant, so I'd like to remind you that at least in the case of quantum mechanics, so the back reaction of quantum fluctuations is what is responsible for most of the mass of the matter we see in the universe. So this was largely the reason behind the Physics Nobel Prize in 2004 to Gross, Wilczek, and Politzer. So this is the back reaction of quantum fluctuations onto the gluon field that gives mass to most of what you see in nuclear physics. So the back reaction of statistical fluctuation is usually not so dramatic, but it does modify Navier-Stokes equations near liquid gas critical points and in 2 dimensions. So should you care? Should you care about this? Well, it depends on the questions that you ask. So the relationship of hydrodynamics to microscopic physics is like the relationship of classical mechanics to quantum mechanics. Now, quantum equations of motion, they sort of look like the classical equations of motion. So if you solve the equations of motion, okay, you solve the equations of motion. But if you look at correlations, okay, so it's when you look at correlations, that's when the quantum and classical predictions can differ very dramatically. So similarly, if you're interested in macroscopic, long distance correlations, then classical equations of hydrodynamics that ignore the back reaction then can lead to dramatically wrong predictions. And again, I emphasize this is macroscopic correlations, not microscopic correlations. So to give a few examples of things that go wrong for normal fluids, if you try to look at macroscopic correlations, well, if you thought that hydrodynamics is given by differential equations, doesn't work. This power series for frequency as a function of the wave vector doesn't work. Hydrodynamics and the relationship between the Lyapunov exponent doesn't work. The transport, you thought the transport coefficients like the viscosity will determine for you long distance correlation, doesn't work. So incompleteness of classical hydrodynamics is something that has been known in statistical physics going back to 1970s and even to early days of the molecular dynamics simulations. And the way to deal with this is to recast hydrodynamics in a language which is similar to quantum field theory. And there has been a recent revival of the quantum field theory approach to hydrodynamics. Okay, so where does this leave us? Where does this leave us? So for me, this actually leaves me with a dream. So it's a dream of a grand unified theory of hydrodynamics that applies to many different kinds of fluids. It ensures that the equations are sensible in the same sense I talked at the beginning of this presentation. It allows for systematic improvements in the sense that I talked about in terms of convergence, divergence. It actually correctly predicts macroscopic correlations and take all these back reactions into account. It does connect with quantum chaos. And very importantly, it's experimentally verified. So for students, I put down some review papers in here. So the second one is a particularly nice introduction into the recent set of ideas about the grand unified theory of hydrodynamics. So I'd like to end with an encouragement for students. Okay, so as a student, and I know this from experience from being a student myself and from talking to students now as a faculty member. So as a student, one often tends to think that all interesting questions in physics have been answered many years ago by the greats. And hydrodynamics is an ancient field by modern standards, and people are still trying to figure out some very basic questions in hydrodynamics. So if as a student you work in a field that is less than 200 years old, well, do not lose hope. There surely are many fundamental things left to discover. Thanks for listening.
All right, thanks a lot. Very nice talk. Okay, so we now have some time for questions. As I said before, please, if you can, raise your hand using the button at the bottom, and I'll call on you, and then you can ask your question to Pavel. So do we have questions?
Yes, I do have a question.
Please.
Yes. Well, I couldn't see how I raised my hand, so anyway, I just unmuted my phone. No problem. So you had the quantum from the classical fluctuations, you went to the quantum Lyapunov exponent. If you start with the classical, is no H bar, so how do you have with quantum forms in there?
Well, it's a good question. I don't think it's there is a fundamental understanding of how this works. Of course, something that's classical is fundamentally an emergent thing out of something that's quantum, right? So even things like the equation of state, the equation of state is a classical thing. But in order to compute what the equation of state is, you need to know about the underlying quantum dynamics. So So the equation of
Yes, if
status.
you want to put phase number of states, you have to put an h bar in there, but that comes afterwards. You can live with a standard equation of state without having to worry about the number of states that you have per unit phase volume, which is given by h bar. So if you don't put h bar anywhere to begin with, because you're doing with only classical things, how does that emerge out of your fluctuations?
Well, quantum mechanics clearly cannot emerge from
Not quantum mechanics, the quantum flux. I may have misunderstood that you started with a quantum Lyapunov exponent came out of purely classical fluctuations. Correct. That's the thing that kind of, I don't have a way of connecting.
Correct, and I think well, it's an excellent question, and I myself do not have an intuitive understanding for how this works. So this seems to be the case in those models, in those holographic models that I talk about, and you can show that it sort of works like that. So there are arguments based on sort of effective field theories that are engineered to describe how this works. So this is perhaps this paper by Blakely and Liu would be the most relevant one to describe this. But I don't know that there is like a simple intuitive argument that will tell you, oh yeah, so that's how it happens. So I would say this paper is perhaps the best reference, and if any of the authors of this paper are in the audience, maybe they could comment.
I certainly don't want to monopolize the discussion here. I saw that the superstring people, or whatever they call it, they found a relation between viscosity and what was that? Viscosity and entropy. Yes. So I went down and took a black body with temperature above m electrons squared, so there's a pair equilibrium. And I can calculate the viscosity now by simply using the mean-free path of photon scattering with the electron, and I got pretty much the same number. So I don't see anything dramatically fundamental there, but it may have to do with some of the stuff you mentioned. Thank you.
Well, so would you like me to comment on the viscosity as well?
Yes, if you want to, yes. I mean, as I said I took a black body with temperature above the electron rest mass so that we have pair equilibrium. We know how many electrons we have in there. And then per unit volume, we can calculate the mean free path. So if I know the mean free path, I can calculate the viscosity. And I know the entropy, so I take the ratio, and I got basically what people got from ADS, CFT, dualities, and so on and so forth.
So was there a question?
No, I mean, I don't see there's been a big issue made out of the fact that this theories can calculate the ratio of viscosity to entropy, and I found that in a simple black body with sufficiently high temperature, so you don't have to put the electrons by hand; they just come out of the flux of the pair production, and you get the same number.
Well, yeah. So one thing I will say about that is that the relationship between the viscosity and the density of entropy in those examples. So this would be an examples. So this would be for fluids that have very strong quantum mechanical interaction, where the notion of the mean free path does not exist, where the notion of a particle does not exist. So the notion of the Boltzmann equation, whatnot, does not exist. And I think it was fascinating that in those examples, you could still find exact answers for what the viscosity is and the relationship between the viscosity and the density of entropy.
All right, thanks for the question.
Thank you. Sorry, I don't want to ask any more questions. Thank you.
So apologies if I mispronounced your name, but we can start with Arkady.
Yeah, it's Arkady Weinstein. Yeah, hi, Pavel.
Hi, Arkady.
No, I'm trying just to follow about this quantum part of of your stories. No, I would say that the main feature of quantum mechanics is that you are going to discrete levels out of continuum, right? I mean, it is the main signature.
Right.
No, particular, for example, you talk about this Lyapunov exponent, for example, right? And it's clear that quantum mechanics make system more stable as compared with a classical system, right? I mean, because of this discretization, right? So you have kind of, you know, different times, whatever. No, in your example, when you discuss this kind of, you know, level crossing, right? Classically, then also in quantum mechanics, you would think that there is a kind of, this quantum mechanical picture of level crossing, right? I mean, that it would be not exact crossing, but it would be some exchange of level, you know, as usual in quantum mechanics. Yeah, so I wonder, in this sense, you know, kind of, okay, so what is your comment on, you know, this quantum mechanical effects in those stories?
Right. So these two things. One is the level crossing in dissipative systems, right? With the, you know, imaginary frequency and imaginary momentum. So both the energy and the momentum have to be imaginary. There's one story about the level crossing in microscopic dissipative systems. And another story is the story about the connection between the sound wave dispersion relation and the Lyapunov exponent. And it's a very natural question to ask. Is there any connection between the two stories? So for example, is the point, you know, the value of the energy or the wave vector where the level crossing happens, is that something that, you know, allows you to extract, you know, that Lyapunov exponent here? And does not happen to be the case. And I don't know why. So when I first started to look at this, so I knew about this, and then I thought, oh, let's look at, you know, this level crossing. So surely this level crossing must happen at exactly the same point that tells you about the quantum Lyapunov exponent, but it does not. And I don't have good explanation for why it is not the case. I was hoping it would be exactly the same, but not. And I as I said, I don't have good intuition behind this. So I think like one is still at a point when there are, you know, calculations, but, you know, the good intuition is something that, you know, one is still trying to build for these things.
Thank you.
Can I ask a question?
Yeah, go ahead. Then.
Alex Levchenko here. Thanks. I have a question, if I may, about your dream. I'd like to clarify a little bit your last slide about this unified picture. So in condensed matter context, we of course can get hydrodynamics from more microscopic approach, going back to kinetic theory, projecting kinetic equation to zero modes, and so on and so forth. You can calculate controllably corrections. It's really a question about how much of technical power you have in those calculations. So why isn't this satisfy your dream? I mean, do you see anything beyond that? I mean, what is actually a statement about this grand unification?
Well, so the examples in kinetic, So there's examples in kinetic theory that that you mentioned are something that would allow you to get hydrodynamic equations themselves.
And corrections and everything. I mean,
right, and corrections to hydrodynamic equations that would not allow you to get a handle on macroscopic correlations.
Why not? They will. I mean, we do know, you know, stochastic processes, Boltzmann-Langevin, and all. It really a question of how accurate you'd like to be with your starting quantum description. I think it's all there.
Right. So if you know how to you know, so Boltzmann-Langevin is just an approximation, right?
Of course, yeah.
So there are, of course, things that are not in hydrodynamics, but something that does contribute to macroscopic correlations, right? So macroscopic correlations depend on things that hydrodynamics is completely blind to. And so what you're saying is that if you have a certain, you know, microscopic theory, then maybe you can solve for everything. Well, of course, if you have even a microscopic quantum field theory and you can solve for everything, then you don't need this, right? So my dream, just to clarify what I mean by a dream, is that my dream is formulated in the language that does not, that is not dependent on what kind of microscopic theory we are talking about. So in other words, when I say apply to many different kinds of fluids, what I mean is that it's an effective theory that does not care about the microscopic details. It could be Boltzmann, it could be, ADS-CFT, it could be, strong interactions, weak interactions, but the procedure of writing down the effective theory, just like, people write effective field theories in particle physics, should not matter. So the only thing that matters are the symmetries, the right degrees of freedom, the correct incorporation of those correlation effects.
Hi, can I?
Yeah, let's have a list here. So, Andrew, you have your hand raised for a while.
I had my hand raised for a while.
Yeah,
We'll
thanks.
Get everyone.
Everyone
will have a chance. Don't worry.
Yeah, very interesting talk. So I'll admit I'm neither a relativist nor a quantum mechanic, but an astrophysicist who found your talk very interesting. I have a couple of simple-minded questions. The first is, to my understanding, the temperature of a moving body that has a temperature T at rest is thought by different people to be either T over gamma, or T times gamma, depending on different definitions and assumptions. So I'm wondering if you have a favored set of assumptions that gives either of those transformations. And the second, possibly related, is I'm very interested in radiation hydrodynamics currently. And so I wonder if for your grand unified theory, if it's necessary to consider radiation and how matter couples to radiation.
Right. So in terms of matter and radiation, so this grand unified theory is should not care for what exactly the microscopic degrees of freedom are. So this could be photons, could be electrons, could be nuclei, could be quarks. So what is important are things such as symmetry, locality. If you are close to a critical point, maybe you need to throw in some, the dynamics of the order parameter, or if you're in a superfluid, throw in the dynamics of the order parameter. But whether you have, photons or electrons, that should not matter. So what does matter, of course, if you are looking at radiation, so is the radiation describable by fluid dynamics, right? So if the mean free path of photons, is huge, there is no local thermalization that happens there. So in which case, hydrodynamics is simply not the right language, right? And if it is not the right language, so okay, so it's not the right language. So for the temperature, so maybe I can make two comments here. So one is about the temperature, of a moving thing. So my favorite one is the temperature that satisfies the Tolman's law, right? So the Tolman's law is the one that is temperature is, is equal to some normalization constant divided by the square root of G naught naught, or of course it's G naught naught in some coordinates. More generally, there's the preferred vectors, that you contract this metric with. And if that vector is a Killing vector in equilibrium, so that's what the equilibrium temperature is. Now, so what I was specifically interested about here in my discussion of relativistic fluid dynamics is the non-equilibrium temperature, right? So those different things that people talk about that you mentioned, they refer to stuff in equilibrium, right? So if you are interested in the stuff that is out of equilibrium, then there is really an ambiguity. So there's really an ambiguity, so you have to choose a convention, you have to choose a thermometer, and depending on the convention that you choose, one can get different mathematically inequivalent equations, and some of them will be mathematically well posed, and some of them will be ill posed.
All right, great. Thanks for your patience, everybody. Rudra, you're next.
Oh, hi. Hi, Pavel. This is a great talk. My question is regarding this. So as you mentioned, hydrodynamics equation, the framework of hydrodynamics usually involves taking variables that are, conserved quantities or broken symmetry variables, and then forming these long wavelength, low frequency equations out of them, as explained in, let's say, a classic book like Forrester's book. But today you showed some very interesting, you made some interesting points regarding the dispersion relation. And I was wondering if that's a consequence of there being additional low energy modes, which are not the conserved quantities or broken symmetry variables. Is that where it's coming from, or is it something different?
So in these examples here, so things that, so things like that, level crossing or the, convergence of the dispersion relation, there were no broken symmetry modes. It's not like a superfluid. So there are no broken symmetry modes. It's just the simplest normal fluid that you can think.
My question was slightly different, which is that are there other low energy modes which are not captured either by conserved quantities or any one of the standard paradigms we have of what low energy modes look like? Is it a consequence of there being some other low energy modes that are not captured by these paradigms?
In these examples, no. So in these examples, at least people believe that they understand what the low energy modes are, and the low energy modes are just the hydrodynamic modes.
I see. Thank you.
Yeah. So it's really there's some kind of interplay between the gapped modes and the gapless modes, and in this exactly solvable examples, they just show up as different branches of the same multi-branched complex function.
Thank you.
Thanks. Next is Rob. You there, Rob? Okay, we'll come back to him if he has a chance later. Ryan, do you have a question?
Yes, I do. Hi, Pavel.
Hi.
Early on, when you were talking about the ambiguity, you were talking about frames, right? Like the Landau frame, etc.
That's right.
Okay. So I just want to understand what it is that you fixed. So by choosing a sensible frame, are you saying you fixed the problem that the Israel-Stewart treatment was trying to address?
Correct. So what I'm saying is perhaps, maybe if I want to be provocative, is, these kind of conventions or frames, people call them frames, these conventions that I was talking about here, so those frames, they could have been invented in 1950s. So if they were invented in 1950s, it's possible that, Israel Stewart would not even be here. I don't know, it's a speculation, it's a provocative speculation, but yeah. So it fixes exactly the same problem that the Israel Stewart was trying to fix.
Yeah. Well, from the perspective of numerics, it's very interesting.
All right, thanks. Sriram, do you have a question?
Your dream slide, if you don't mind. So I just want to come back to this point. What parts of of the dreams that you list here, I can see that standard broken symmetry plus conservation laws plus fluctuations, that is fluctuating hydrodynamics of conserved and broken symmetry modes, meets pretty much all the criteria, the requirements you list here, except possibly the connection to quantum chaos. It applies not only to fluids, but to a wide variety of ordered phases, superfluids, liquid crystals, you name it. The equations are sensible. They aren't classical hydrodynamic equations because they are stochastic. It's like writing down operator equations. But once you do that, it allows the systematic improvements to the extent that you can do a good normalization group or something. You calculate correlation functions. And the only thing I can think of is connection to quantum chaos. So is that the only thing that's missing, or are there other bits of your dream that I'm not understanding?
Right, so the connection, you're right. So the connection to quantum chaos is definitely one of them. So another one is the systematic improvements in the sense that the conventional stochastic hydrodynamics it sort of, postulates, things about, the noises, the Gaussian noises, which, in general, not Gaussian. And stochastic hydrodynamics does not tell you how to go beyond that and how to do it systematically in a way that so fluctuation dissipation theorem is satisfied. So this is something that, this formalism, is described in this review paper would address. So, but the conventional stochastic hydrodynamics would be blind to those effects. So, and this also translates to macroscopic correlations, because in those cases, stochastic hydrodynamics would incorrectly predict certain macroscopic correlations.
I see. So I can find more about those in this paper by Glorioso and Liu, is that right?
That's right. It's a set of lecture notes or review, right?
I see. But you'll agree that the stochastic hydrodynamics of broken symmetry phases does cover a fair fraction of what you listed on this.
Right. So I would consider that to be like a starting point or the groundwork for that ground unified theory. That's right, yeah.
Okay, all right, thanks.
Great, thanks. So next we'll do Dietrich, and then I have a few questions from the private chat that I can invite. So Dietrich, do you have a question?
Yeah, so one question about the dream. What if the gradient expansion is not analytic? Is that included in your grand unified theorem? And a related question, often we have non-convergent series expansions, but we don't care because they're asymptotic. Is that relevant in this context?
Right. So, so the first question about series being the function being non-analytic. So this is supposed to be included in this grand unified theory, because if something is not analytic, so that's usually for a reason, right? So, and so what is the reason? So the reason is that, you normally would miss some of the, degrees of freedom. And in the example that, I showed here, so this would be an example of what the modes in a fluid do in those exactly solvable examples. And as a result of those stochastic fluctuations, which actually would be captured at the most elementary level by the stochastic hydrodynamics, this picture would be different. There would be all kinds of branch cuts, right, in this picture. And these questions about the analyticity of expansions like this, so they would not make even sense, because there would not be, a simple, polynomial expansion for, energy as a function of frequency. So that would be captured by the fluctuating degrees of freedom. And the other one is about the asymptotic nature of the expansion. And that I really don't have much to say about, except maybe I can make one comment, is that this expansion, it looks differently whether you work in the Fourier space or whether you work in the real space, right? So you can have a perfectly, sensible expansion in momentum space. But if you ask, similar or related questions in real space, then you would find expansions that are not convergent, but are asymptotic. Yeah.
Thank you.
Okay, so now we had a question from Andre.
Thank you. Hydrodynamics is an ancient subject, and its history is rife with paradoxes. So what would be a kind of minimal paradox in relativistic hydrodynamics? If you say that there are inconsistencies between equations, there must be a simple way to formulate a paradox about this. What kind of experiment would show which equations are right?
Well, yeah, so the way I like to think about this, I like to think about this not in terms of the paradoxes, but in terms of what are the right equations that we are solving, right? When people normally talk about, hydrodynamics of Galilean fluids, so that's the context in which many of these paradoxes arise, there is no question about what the equations are, right? So everybody agrees on what the equations are. And within that framework, you can now ask about paradoxes. So for relativistic fluids, so the situation is sort of similar to relativistic versus non-relativistic quantum field theory, right? So if you look at non-relativistic quantum field theory, then the structure of the propagators is such that the ultraviolet divergences are much more benign than they would be in relativistic theory. So, and the same kind of happens in hydrodynamics. So in relativistic hydrodynamics, so the effect of those, UV degrees of freedom, it kind of has much more dramatic effect than it does in non-relativistic hydrodynamics. And so it looks like, so in non-relativistic normal Galilean hydrodynamics, there is surely some UV physics that is sitting in those equations, but that UV physics does not do anything bad. Whereas in relativistic hydrodynamics, that short distance, short time physics that creeps into the macroscopics, it does do something bad. So in a sense, the theory always has to be formulated with a cutoff, even at the classical level. And how to remove that cutoff, and how to ensure that the low energy physics is, so to say, cut off independent, even within the framework of classical, purely classical hydrodynamics is a separate question. So yeah, so for me, the question really is, what are the correct equations? And then what is the structure of the cutoff? And the structure of the cutoff is, of course, something that's not universal and something that probably will be sensitive to the microscopic details of the fluid.
All right, thanks. Jung Ren, do you have a question?
Yes, can you hear me?
Yes.
Yes.
Yeah. Yes. Thank you for such a nice talk. I really like it. And so I have a naive question. So you said that all the hydrodynamic equations we have so far are approximations. Yeah, but then so how much predicting power all these theories have for, say, turbulence? And would the second order equation will work better or not? Can you comment on that?
Well, I guess there are people in the audience who are much more qualified to answer the question than I am. So if I don't know if any of the experts on turbulence want to comment on that questions, maybe, I don't know.
Any comments?
I really like your talk a lot because I do think the Navier-Stokes equation is incomplete. Something wrong with that. I'm really glad to hear that.
So that particular question that you asked, I don't know the answer to that, and I have not thought about it.
And I think that I'm actually a soft matter physicist, so it really worries me if the fluid mechanics, all the theories could not predict the highly dynamical situations such as fluid turbulence or chaotic situation. Then how much can we understand all this kind of physics?
Right. Yeah. So what you are maybe if I rephrase the question in a language that is kind of more familiar to me, is that why is it that within the framework of macroscopic effective theories, there is a separation of scales, separation of short distance scales and long distance scales, and to what extent is it guaranteed that the short distance physics isn't going to creep into the long distance physics? I would say it's far from guaranteed for these, macroscopic systems that are described by fluids. And, you know, we know this very well, you know, like if you look at, you know, the waves, how they break, you know, initially you start with, you know, very, very small gradients, but then you may develop, you know, very large gradients at later times. So, but, you know, the exact degree of, you know, how exactly that interaction happens, I do not know much about that. So if anybody in the audience would like to comment, that'd be great.
Just a follow-up. So just following your thoughts, can I just say that, say, Navier-Stokes equation is just a mean field theory. So that's why
I would totally agree with that, yes.
Yeah,
yes.
We couldn't take care of all the fluctuations.
Yes. Yes, I would agree.
Thank you, yeah.
All right, we had a question from Philip. Are you there, Philip?
Yes, still here. Let's see. Can you hear me okay?
Yes.
Yeah.
Let me get rid of my background. Yeah, so that was a great talk, very clear. Thank you for that. My question concerns the part one, where you derive some relativistic fluid equations.
Mm-hmm.
And the question is, so one way of getting fluid equations is by taking moments of an underlying kinetic theory,
yep.
and then trying to effect a closure of some kind.
Yep.
And I'm wondering if you have done this, you know, something along the lines of the Chapman-Onskog kinds of expansions that are done for classical fluids.
Right. So indeed, this can be done. It will not be this Chapman-Onskog expansion. It will be a slightly different expansion. But if you look in this paper, the first paper, 1708-06255, yes. So that paper has a discussion of how exactly that is done. So if you look in this paper, so there will be details.
So part of this relies on ordering of a collision operator of some kind. And so you would need some kind of relativistic collision operator in order.
That's right. Yep, that's right.
And you have one. Which one is it?
Well, it depends on what exactly the degrees of freedom are, right? It's something that is determined by, you know, by the scattering amplitude of the elementary relativistic particles.
Yeah, so you derived in the end a set of fluid equations of some kind. Are they
That's right.
a general form that are valid for a variety of collision operators, or are they?
That's right.
I see. So it's more of a meta theory than a theory of a specific interaction.
Correct. Absolutely correct.
And then usually in the types of orderings that people do, the collision operator is the dominant term, and then you have something that is in local thermodynamic equilibrium of some kind. That's how normal fluids are derived. So that's one kind of small parameter expansion you can do. It would seem to me that depending on your interactions, that the kinds of collision operators you have, you might have different kinds of expansions depending on different kinds of collision operators, which makes me wonder how you can there must be something common to your meta theory that does this.
Well, so perhaps the best way to think about it is not even to think about the kinetic theory, but just to think in terms of any effective theory. Right? So in any effective theory, say you write down constitutive relations for your fluid, right? You just write down all the terms that are allowed by the symmetry.
Yeah, so that's a way to derive a macroscopic model.
That's right.
I guess my question is really about what underlies it. I mean, ultimately, you could go back to a BBGKY hierarchy.
That's right.
Develop different kinds of moment closures from that.
Right.
This is normally how you find a deeper understanding of a fluid theory.
Right.
I'm just wondering to what extent you've done that with your new fluid equations.
Right. Yeah. So as I said, so if you look at this paper, so this is not my paper again. So if you look at this paper, 1708, so there will be details there. But what I will say is this. So the main inconsistency the root of the inconsistency in the standard, Landau-Lifshitz or Eckert hydrodynamics is really this, is the instantaneous reaction of temperature. And so the way it is fixed is by, the way I phrase this is by introducing, sensible thermometer that has some finite response to the changes in energy. So there is some quote unquote relaxation time that is a parameter of your thermometer. Now that relaxation time is not something that you can calculate from kinetic theory. So that relaxation time shows up as an integration constant for one of the zero modes of the collision operator. So it will be an undetermined constant. So which goes with this analogy that I gave, that those things really should be thought of as regulators of the effective theory, right? So any effective theory has an ultraviolet regulator that is not determined by the low energy dynamics. So those extra ingredients, they would be like ultraviolet regulators that are not calculable, that you can see them in the kinetic theory, but they're not calculable in kinetic theory.
Well, there are many things in kinetic theory that you can't calculate, but, but it seems to me that you might be able to get some information out of kinetic theory about those, depending on how far back you go. I mean, ultimately, there's a more primitive description of all of this. And how quickly a thermometer relaxes must be in a kinetic theory somewhere. It's, you may be projecting it out when you're doing what you're doing to get the fluid theory, but that's just something that you chose to do.
Right. So so what you can do, of course, is you can go to higher order in the gradient expansion. So this was trying to fix the problem at the lowest order.
Come out of the interaction in the kinetic theory.
Right. So as I said, so if you work consistently, to a given order in the derivative expansion, then to a given order in the derivative expansion, so those extra ingredients that are needed to make the theory sensible, they are visible, but they're not calculable. They're visible as integration constants.
Okay. Anyway, I'll stop here. Again, it was a really great talk and very inspiring. Lots of very thought-provoking. Thanks again.
Thanks for the question. So let me try Rob again. Are you there, Rob?
I'm there. I just didn't unmute earlier.
So okay.
I regret this. I hope this is the last one. You've got a mathematician here who also is interested in Einstein equations, and you got the right slide up. And so this is a completely toy question, and so feel free to just throw it away. But suppose you turned off all the other couplings. You just had essentially, geometric dynamics, the Einstein equations, but with a fluid of tiny black holes, or black holes, whatever size you like. And interaction both by the equation. So gravitational radiation and whatever, purely geometric. You've thrown away the background Minkowski space-time. You can't really do the Fourier expansion exactly anymore. Maybe you can do it approximately. Has anybody ever played with that? It might be fun. It's even in a 2+1 dimensional version, if you take the Einstein equation seriously. And that's meant to be a fun question. Feel free to throw it out if you don't want to even. Be a nightmare rather than a dream. Okay.
So I want to make a comment on this, is that, the assumption, the underlying assumption that goes into hydrodynamics is that there is some locality of interaction. So there's some, in thermal equilibrium, there is some kind of finite correlation length. And if that correlation length is not finite, then you know exactly why this happens. It may happen due to magnetic fields, like in MHD, or it can happen due to order parameter, as in superfluids. Of course, if you just have normal electromagnetic interactions in the presence of charged matter, the electric fields will be screened. So again, that's sort of the short range of electric interactions is sort of maintained. Now, if you have gravitational interactions which are not screenable, right? So then I would not know how to formulate an effective theory. Maybe some people have thought about it. I have not. So I really do not.
That's a fair answer. I'll assume dominant energy condition, yes, a positivity at least, but I agree that it was for a small number of particles, not Avogadro's number of black holes, but something bigger than 2. I think it'd be a fun computer experiment for someone to try it.
Well, I mean, of course. I mean, if hydrodynamics is supposed to be, something that exists that describes, very, long distance scales, then at long distances we have the Jeans instability, right? That's going to settle in. So one of the underlying assumptions of hydrodynamics is that some kind of notion of local equilibrium. This means we have to be able to somehow define, the equilibrium state somehow. And if you just have, I guess, some black holes, then I say, okay, let's wait a little bit. They all collapse to one big black hole. And
well, at the galaxy scale, obviously, we've been around for a while. So you mentioned the Jeans instability. I mean, obviously we don't need general relativity to explain the galaxy. Maybe there's some era when we do that comes into either the distant past or the far future. Anyway, thanks. It was great talk. I appreciate it.
Thanks. So we have one more question from Matteo, and then we'll be finished. Matteo, are you there? Nothing. Well, he sent me a question in chat, which is assuming frequency omega real and k and momentum k complex, and assuming omega complex and k real give 2 different dispersion relations, is it a problem given that the equation relating omega and k is from the same theory and is unique? So I think he's asking about real versus complex k and omega.
Well, I mean, it really boils down to this equation, right? So there's just one equation, and the question is what you do with this equation, right? So how you find solutions. And this comment was basically when we teach our students, we usually do one or the other, right? We take omega real, then this equation has complex solutions for k, and when we take k real, then this equation has complex solutions for omega. But there are also solutions to this equation when both omega and k are complex. So if you wish, this would describe a curve in the complex C2 plane when you have a single function of 2 complex variables, right? So this describes a curve in the complex C2 plane, and these 2 special cases would be like 2 special points on that curve.
Great. All right. That's it. Thank you, everyone, for listening. Thank you for your patience and great questions during the question period. Thanks to Aspen Center for hosting, and thanks to Pavel for a great talk. And see you next time.
Yeah, thanks, everyone.